Yalamat everyone and welcome. On behalf of the Ismaili Tariqa and Religious Education Board for Canada and the Aga Khan Education Board for Canada, I would like to welcome you to the Horizon Conference webinar series. My name is Alia and I will be your moderator for today. Today, in our second webinar series, we are excited to have Dr. Farzana Meru joining us to discuss how our planet's born. I would like to quickly acknowledge our Horizon Conference and webinar team. As mentioned, my name is Alia Remtolat Rani, and along with Naz Virji Babu, we are your Horizon Conference team co-leads. Joining us today, we also have our webinar technical coordinator, Aris Remtola, and our support team comprising of Nadim Remtola and Imran Kaku. So we begin with a speech delivered by His Highness Aga Khan at the commencement ceremony of the American University in Cairo, Egypt on June 15, 2006, and I quote, "In Islamic thought, beauty and mystery are not separated from intellect. In fact, the reverse is true. As we use our intellect to gain new knowledge about creation, we come to see even more profoundly the depth and breadth of its mysteries. We explore unknown regions beneath the seas and in outer space," unquote. The Horizons Conference webinar series was created to bring together scholars and other experts to be able to share their knowledge and their expertise. Last week, we discussed and learned about Antarctica, and this week we're going to explore how planets are born. We really hope that this webinar series allows you to learn, to explore, and to inspire you to understand creation in all its forms. So let's begin. I'm very excited to introduce our guest speaker, Dr. Farzana Meru. Farzana is an assistant professor and Royal Society Dorothy Hodgson Fellow in the Astronomy and Astrophysics group at the University of Warwick. Her research focuses on planet formation, planet evolution, and disk formation, mostly using a variety of numerical techniques. Farzana, we would like to welcome you and thank you for taking the time out of your schedule to be with us today.
Thank you very much, Alia. Yalimadad, everybody. It's an absolute pleasure to be here to talk to you, to take you on a journey through our universe over the next 30 to 40 minutes. And in particular, what we're going to do during this time is to try and answer this question that you see on your screen: how are planets born? But to begin with, what I would like to do is to ask you a little bit of a trivia question and have a think in your own minds for a few seconds the answer to this. Which of the solar system planets can fit in between the Earth and the Moon? Is it Mercury? Is it Mercury, Venus, and Mars? Is it Jupiter and Saturn? Or is it every planet in the solar system except for the Earth? So hopefully you've got an answer or a guess in your mind. It is, in fact, every single planet in our solar system except for the Earth. What you're seeing on the very left-hand side of this image is a little picture of the Earth. On the very right-hand side, that little tiny dot that you can see is the Moon. And what you see is that every single planet in every single other planet in the solar system can fit in between the two. Now, when I first heard this fun fact, I was actually it was just completely mind-boggling to me, because the Moon feels so close at times. We can see some of the details on the surface of the Moon, yet there appears to be so much space between us and the Moon. So this just gives us some perspective on just how much space there actually is out there. And continuing on with with gaining a little bit of perspective, I just want you to have a think about the countries that you're in. I've got the map of Canada here. If you're elsewhere in the world, have a think about how large your countries are. Even where I am in the UK, it takes quite a bit of time, a few hours for us to get from north to south. That's big for me. And we can put that into a little bit of perspective. So despite how big we might think our countries are, in fact, they just take up a small amount of space on the surface of our planet Earth. And in fact, we can put this into perspective a little bit more. So the Earth is just a small part of our huge solar system. So what you see in this diagram here on the yellow part on the very left-hand side, that's representing the sun. And what we're seeing here are the planet locations in our solar system to scale. The sizes are not to scale, but because the planets would be much too small, they would just be dots on this picture. But what you can see is that around the sun, you have the 4 terrestrial planets: Mercury, Venus, Earth, and Mars, and they are orbiting the sun. And we go further out to the right in the solar system, and we see Jupiter and Saturn. These are our gas giant planets. And then we go even further out in the solar system, and we have Uranus and Neptune, which are our ice giants. Now, the astronomers typically use a distance scale, which is quite different to what other people use. We use what we call the astronomical unit, and I'll use this a few times today. So I want to start by just explaining what this is. So an astronomical unit is the distance between the sun and the Earth. So just to put this in a little bit of perspective, Neptune over there on the right-hand side is at 30 astronomical units, meaning it's 30 times further away from the sun than the Earth is. So that gives you a little bit of an idea as to sort of just how big our solar system is. Well, in fact, we can put that into perspective. This image that you see on the right-hand side is an artist's impression of what the Milky Way Galaxy looks like. Now, the Milky Way is the galaxy in which our solar system resides. And you can see that this is a huge, huge galaxy, and our solar system is just a tiny, tiny part of this incredibly vast, majestic, astronomical piece that you're seeing. Now, in fact, the size scales get actually even more mind-boggling. So what you're seeing here on the right-hand side is a real image that was taken by the Hubble Space Telescope. This is what we call the extreme deep field. And what this is, it's the deepest image of the sky that's ever been taken. And it reveals the faintest and most distant galaxies that we've ever seen. Now, what you're seeing here are all of these specks of light are essentially are galaxies, and there are thousands of galaxies just within this one little image. Now, when we're looking very far out in the universe, what you're doing is looking at older parts of the universe. So the furthest galaxy that you can see in this picture is in fact was formed just 450 million years after the Big Bang. Just to put that into perspective, the universe is 13.7 billion years old. So we're actually looking really far out into the universe at some of the galaxies that were first formed shortly after the Big Bang. Now, this image was actually taken when the Hubble Space Telescopes looked out at a particular patch of the sky. So what you're seeing in front of you is the moon, and in the square in the middle with XDF, the extreme deep field, that is that image that we were seeing. So imagine this. We've only looked at a small portion of the sky in a lot of detail, and we're able to see thousands of galaxies. If you were to multiply that and look at the whole of the sky that we see around us, not just this tiny fraction of the sky that we did look at, there would be something like up to 100 billion galaxies in the universe. And that's if we were to consider that whole area. Now that's just the galaxies that we have been able to see. There are more distant galaxies that we weren't able to see. So it's possible that in fact that number of galaxies is even larger than 100 billion. So now that we've gone to sort of the deepest, darkest depths of the universe, let's actually come back to what we are focusing on. So to astronomers, planets are actually pretty small objects compared to the kind of thing that I've just shown you. But nevertheless, they are interesting in their own right. So much so that an entire field of research has in fact been dedicated to understanding these amazing objects which you can quite often see in the night sky. Now, what you see in this artist's impression of the solar system here are 8 planets. Now, many of you will recall a time when we were actually taught at school that there were 9 planets in the solar system. And this is an example of how research and how our understanding evolves over time. So the sun is a star, and the planets in our solar system orbit around the sun. And just like the planets orbit around our star, there are other stars out there and other planets that orbit around those stars. And we call those planets extrasolar planets, or for short, we might call them exoplanets. So now I have another question for you. Have a think about this. How many exoplanets do you think have been discovered? Is it less than 100? Have we discovered somewhere between 100 and 1,000? Or is it somewhere between 1,000 and 10,000? Or in fact, have we discovered more than 10,000 planets? So you'll actually see the answer to this question in just a minute at the end of this movie that I'm going to show you. This movie actually shows you the number of exoplanets that have been discovered over time. Now, what you're seeing, this bright U-shaped band in the middle, this is the Milky Way Galaxy. Now, as I showed you in one of the images before, the Milky Way is in fact a flat disk. But what we've done in order to take this image here is to take pictures of the Milky Way, essentially taking many pictures of a curved sky. And what we do is to stitch these pictures together and projecting it onto a flat image, what you see on your screen here. So that's why instead of the Milky Way looking very flat, it actually looks a little bit curved. Think about your panorama function on your smartphone. When you're taking a picture with that panorama setting and you move your camera around, you actually see that it distorts the picture the final picture that you get. And that's simply because it's a curved picture that you're taking, but you're projecting it onto a flat screen. So what you see at the very top of this this movie here is the year and the number of exoplanets that have been discovered. So I'm going to start playing this movie now, and you'll see that the year and the number of exoplanets goes up over time. In the early 90s, that is when we first observed extrasolar planets. And you can see that by about the year 2000, we really still only had a small number of planets that had been discovered. And you'll see lights appearing on this movie, and these lights are where the planets have been discovered on the night sky. Now, this field has grown incredibly, incredibly rapidly. If you just think about the fact that 30 years ago, we actually only knew of the planets in our solar system. And now, even last year, there was in fact a Nobel Prize, or half the Nobel Prize in physics was actually awarded to two astronomers who had discovered one of the first extrasolar planets. There have been a huge number of telescopes on Earth and in space that have been dedicated to detecting planets and really trying to understand the properties of the planets, such as the mass, how large they are, and what these planets are made up of. You can see in the sort of the top left point, hopefully you can see my mouse, there's a huge cluster, a blue part of this movie, where you can actually see a bunch of exoplanets that have been discovered. These were discovered by the Kepler spacecraft, which went out into space specifically and was specifically designed to actually look for these planets. And it completely revolutionized things. So you can see now, 30 years on, at 2019, we've discovered over 4,000 extrasolar planets. This is an incredible finding for our research field, and this cannot be done without some of the dedicated instruments that have been developed to do this. So the image that you see in the upper left and upper middle are examples of two space missions that went out to observe planets in the universe. And then the bottom left and bottom middle, what you can see are two ground-based telescopes. So we use both space-based and ground-based instruments to actually observe these planets. But none of this can happen without some incredibly powerful computing facilities. So the two images you see on the right-hand side are very large-scale, what we call supercomputers. And these are dedicated to understanding the observations that we see, but then also they're there to help us understand the theory behind planets, behind the properties of planets and how they formed. So we can take a little bit, we can just take a little bit of a step back, because actually what I've showed you is that we've observed more than 4,000 extrasolar planets, but there are in fact many planets that have not been discovered. So let's actually come back to this idea that there were 100 billion galaxies in the universe, thereabouts. This is a number I put up a few slides back. And if we think that every one of those galaxies might be like the Milky Way, and in every one of those galaxies there may be many, many stars around which planets could form. If we assume that they're a little bit like the Milky Way, well, in the Milky Way we have about 100 billion stars. And we actually know from observations that we expect to have about one planet per star. So there are in fact stars which don't have any planets at all. There are other stars which have many planets, a bit like our solar system. If we multiply all these numbers together, what we end up with is this many planets in the universe. I didn't even know how to actually say this number. I had to look it up. This is actually 10 sextillion planets. And this is, if we just take a moment to actually look at how big this number is and just think about what this means that there could be an incredible number of planets out there in the universe. So I now want to ask you another question. I want you to have a think about whether the solar system is a typical planetary system, true or false. So what I'm going to do is to show you a movie of a number of planetary systems that have been detected by the Kepler spacecraft. Now, this is quite a busy plot, so I'm going to walk you through it before I actually play the movie. What you're seeing here are planets orbiting, planetary systems that are orbiting around. So the circles that you see are the orbits of the planets. And each sort of set of circles is a planetary system that has been observed. And these planets are either, the sizes of the circles represent the sizes of the planets. So the very small ones are more like the small planets like Mercury, the larger ones are like Jupiter. And the colors that you see on the screen give you an idea of how hot or cold the planets are. So the red ones are very hot and the blue ones are very cold. And in comparison, what you're seeing in the center is the solar system planets. So in fact, actually the four dotted circles that you see in the center are actually Mercury, Venus, Earth, and Mars. And then if you look further out, we actually see the orbit of Jupiter, again another dotted line, and then another line further out that you can now see is Saturn. And what you can see very clearly from this image here is that all the planetary systems that we've observed are very, very compact. They're much, much smaller than the size of the solar system. And so what this is telling us at the moment is that we don't think that other planetary systems are like the solar system. We think the solar system is actually quite different and unique. Now, this is an idea that we have at the moment, but this idea could change in the future, of course, as more and more observations come out. And just to give you more of an idea of how diverse the planetary systems are, I've picked out a couple to show you. So what you're seeing here is an animation of one of the systems that was observed a couple of years ago. So what you see are 7 planets orbiting around the star. These are Earth-sized planets, so they're very, very small. And just to put this into perspective, they're incredibly compact, very close to their central star. So Mercury's orbit is at about 0.4 astronomical units. Well, these are closer to their star than that. They are 10 times closer to their star than Mercury is to our sun. On the other end of the scale, what you can actually see are planets that are incredibly massive and very far out. So the video that you're seeing on the right-hand side is real observations that are taken using telescopes. And what you see in the very center, you've got the star. Hopefully you can see my mouse. Just to the left, upper left, you can see one of the planets. A second planet is just here up and to the right. A third planet is down into to the right. And then the fourth planet is just to the right of the star. Now, these planets are incredibly massive. They have 10 times the mass of Jupiter. And the outermost planet is incredibly far out. It's at 67 astronomical units. So just to put that in perspective, remember that Neptune is at 30 astronomical units. So that outer planet that you see here is more than twice the distance that Neptune is in our solar system. So this gives you an idea of just how diverse the planets are and how diverse the planetary systems themselves are. So when we're thinking about planet formation, it's very important for us to think about the environments in which planets form. This bright band that you see across your screen is the Milky Way. And what we're going to do is to have a fly through the Milky Way, and we're going to look at a particular region called the Orion Nebula. So this is a region of the sky where there are stars forming. And this visualization is, in fact, there's a little bit of artistic license in this, but largely the data that's used to actually produce this visualization comes from 2 telescopes. The first is the Hubble Space Telescope, and this looks at the visible light, so it's the light that you and I can see with our eyes. And the second space instrument is the Spitzer Space Telescope. So this actually looks at the infrared light. So we cannot see this light with our eyes, but we can detect the heat, essentially, that's coming off using this space telescope. And what we're doing is we're now flying into the Orion Nebula, and the sizes, the brightness, and the of the stars and the locations of the stars are taken from real observational data. This Orion Nebula is made up of gas and dust. And what you can see as we get towards the center of this nebula is that it becomes incredibly, incredibly bright. So if you were to go outside and you had no artificial light in your back garden and you were to take a book outside, you would not be able to read it because there would not be enough light. But if you were to take that same book and you were to go into the middle of the Orion Nebula cluster, you would have enough light from just the brightness of those stars that you would be able to read your book. So having gone through that region where there are stars forming, we can now start to think about how the stars form and ultimately how planets form. And to understand how planets form, we do need to understand this backdrop within which they form. So here what you see is something called a molecular cloud. This is a simulation now. This is not real observations. These are computer models that have produced this. And these clouds are made up of gas and dust, and what's happening is that they're collapsing in various different parts to form stars, and the stars are interacting with each other. Some of them kick each other out, but you also at the same time start to get disks forming around the stars, and you see this in the bottom right corner with one particular star that has managed to form a disk around it. Now, this disk is what we call a protoplanetary disk. So this is the disk in which planets would form. They're made up of gas and dust. Typically, they're about 100 astronomical units or a few hundred astronomical units. Just recall that Neptune is at 30 astronomical units, so we're talking about something that's much larger than the extent of our immediate solar system. And what you're seeing here is an artist's impression, but I'm now going to show you some of the first images of protoplanetary disks, of these planet-forming disks. Now, they were incredibly revolutionary at the time when we observed these. This was back in 1995. What you see in any one of these squares, what you see at the center is a bright star. And then you see a dark patch around the star. And that dark part is dust and gas around that star. And this was the first indication that these disks existed. Now, that was in 1995. Things have changed since then. And in the last few years, what we've managed to do is to develop incredibly high resolution instruments that can actually observe these disks and look at the detailed features in them. So what you're seeing appearing on your screen are examples of real observations. The colors are not the colors of the disks, they just represent the brightness of the disk. But what we see is many of these have bright rings, many of them have gaps in them. Some of these gaps are where we think planets could be forming. You see spiral structures. If you look at the black and white one in the bottom left corner, you can see lovely spirals. If you move towards the right, we can see this blue image, which has got a ring, but then also sort of a crescent shape. All of these features are giving us clues as to how planets could form and interact with this disk. In fact, it's even possible that planets may have already formed in these disks. Now, astronomers work on these kind of images day in and day out to try and understand the processes that are going on in these disks and how planets can actually form. I'm going to pick out one of these images. This was one of the first images made that was produced with one of the most recent groundbreaking instruments. And what you see are these amazing bright rings and dark lanes. And we think that there could be planets in these. Now, just to give you a little bit of perspective, this disk is located 30 million astronomical units away from us, right? So that is 1 million times further away than Neptune is. So it's amazing when we can actually think about the fact that the telescopes are so powerful that they can observe some of the finer details that you can see in this image. Just to give you some perspective, if I if I was able to use that telescope where I am here in the UK, I would be able to easily see a bicycle wheel in New York from the UK. That is how powerful these telescopes are. So I've talked about the environment in which the planets form in, but how do these planets actually form? So there are two ways in which we think planets can form. The first is called core accretion. And essentially what happens is that the dust in these disks comes together. What you see in the background is the star, and you can see dust orbiting around this star. And there's also gas orbiting around it. Now the dust is actually colliding together. It's in some cases, the collisions will actually mean that the rocks break apart. But in other cases, the collisions will actually mean that these rocks will actually grow larger and larger. And they'll become so sufficiently large that gravity will start to take over and attract more and more dust onto it, until eventually it forms a terrestrial planet, a bit like the ones in the inner part of our solar system. Now, if these planetary cores become large enough, they can in fact attract gas onto it so that they end up forming a gas giant planet. So this is the first way in which planets form. It's where the dust comes together first and then the gas can come on afterwards. The second mechanism is where you have the opposite happening. So the gas controls things first and then the dust plays its part afterwards. So what you're seeing here is a simulation of a very young planet-forming disk. You see these beautiful spiral structures. And what happens is that eventually these spiral structures actually become quite unstable, and they'll break apart into little gas balls. Hopefully you can see my mouse, where you can see that I'm pointing to some of the gas balls in the very outer part of this disk. These gas balls ultimately end up having dust going into the center of them to form a planetary core. So this is the second way in which we think planets can form. Now, why is it actually important for us to observe these planet-forming disks? I've put 3 examples of disk observations that we're seeing. And now the planet formation process takes up to about 10 million years. So it's simply not possible for us to actually observe the whole process of planet formation from start to finish. What we have to do is to observe disks at different ages in their evolution. And what we're essentially doing is these images are giving us clues. They are snapshots in time of what a disk would look like. And ultimately, what we have to do is to take these pieces of a puzzle and try and piece them together and try to understand what is going on in these disks. And the way we can try to piece them together is by running computer simulations. So what you see on the bottom in the jigsaw puzzles are images that have been obtained from computer models, where we've tried to model the whole planet formation process around the central star. And what we can do is then compare those to the observations to help try and determine what the evolutionary sequence would be. So when we compare them to observations, we can start to fit the jigsaw piece puzzles together. And these computer models can tell us the whole story of how planets can form and evolve. Now, we certainly haven't completed the jigsaw yet. There's still a lot more to do on this, but this gives you some idea of just how we put the observations and the theory together. Now, I'm going to give you more examples of how observations and simulations can actually move together. So the image that you're seeing on your screen right now is a real observation of one of these planet-forming disks. And you see these beautiful, large-scale spiral structures that have been that have been observed. Now, what the theorists have done is to run simulations. So this is a hydrodynamical simulation. This means that we're essentially modeling the flow of gas and dust in these disks. And what the theorists that looked at this study did was to say, well, actually, there is, if you were to put a planet where that green circle is, this would actually generate the two-armed spiral structures that you're seeing, which look very similar to the observations. So then they can actually say to the observers, hey, our prediction is that you should see a planet at that distance from the central star. Why don't you go out there and actually observe it? So that's an example of where the observations have sort of informed the theory. There are other examples where the theory has informed the observations. And this is another example of another one of these hydrodynamical simulations, of this time of a planet moving in its disk. And this is a process that we expect to happen. And what we can then do when we actually take these simulations, we can say, right, if you were to take that disk and we were to put it incredibly far away out there in the universe, and we were to observe it with one of the telescopes that we have, what would it look like? And what you see in the bottom left is the prediction. So now what we can do is to say to observers, hey, we now have an observational prediction for what this particular process would look like. And if you were to then go out there and look at the protoplanetary disks, you would, and if you were to see these kind of features, perhaps this tells you that there is a planet moving in that disk. So this gives you an idea of just how important the observations are, but just how important the theory is, because the theory and the simulations are what underpins it all. Without this, we cannot make sense of the observations. So where are we at now? So we've had a bunch of instruments that have actually been developed over time to try and make sense of the universe. 30 years ago, we didn't know of planets outside of our solar system. So in just 3 decades, we have come incredibly far forward. Now, we haven't solved the planet formation puzzle yet, but many of these telescopes that are being designed now, the telescopes that will be used in the future, and also the supercomputing facilities will help us to understand just how planets are born in much more detail. So what do we think will happen in the next 30 years? So from an observational perspective, the aim is really to directly image an Earth-like planet near its star. This, just to put this into perspective, this is an incredibly, incredibly challenging task. Imagine if you were looking at a firefly and it is 1 millimeter away from a lighthouse. What you're trying to do is to directly look for that firefly. It is really hard because that light from the lighthouse is overpowering the firefly. That is exactly what we're doing when there's an Earth-like planet near its star. It is incredibly hard to actually see that, but that is the goal. From the theoretical perspective, we really want to understand how the planets that we observe originated, so how they formed. So we really want to try and understand that planet formation puzzle in much more detail. So will we find another Earth? Will we find evidence of life? Is our solar system normal? Before we found exoplanets, we thought the solar system was very typical, and the last 30 years have completely changed our view, and it may change again in the future based on new evidence. There's a lot still to discover. So what I would like to do is to leave you with this very final thought from Ethan Siegel, where he says that the universe is out there and it's waiting for you to discover it. So with that, I would like to thank you ever so much for your attention, and I would be extremely happy to take any questions that you may have.
Thank you, Farzana, for such an exciting and interesting and fascinating presentation. We will now take some questions. We have a lot of questions coming in, so we're going to try and get through as many as we can. We do apologize in advance if we're unable to get to your question. So we'll begin with this concept of light coming from many light years away. When we see this, are we looking back at the past? Are we looking back at history?
Yes, so essentially we are looking back at the past. We are looking back at history, because what's happening is that the universe is expanding and it's moving away from us, and the light that portion of the universe, let's say a distant galaxy, emitted many years ago, is actually taking time for it to travel towards us. So in fact, and it depends on how far away it is as to how long it actually takes for that light to travel. Now, if I can just put things into a little bit of perspective closer to home, the light, when we're looking out at the sun, what we see when we're looking out at the sun is actually what was going on 8 minutes ago, because it takes 8 minutes for that light to travel from the sun to the Earth. And in that same way, when you're looking at a distant galaxy, you're actually looking at it earlier in time rather than at this moment in time.
Awesome. Our next question is, can you explain what you mean by dust? Does it mean that over the years, all the pollution from Earth, does it play a part in this?
Okay, right. So that is a very, very good question. When we refer to dust in the out there in the universe, what we're actually referring to is anything any solids that are other than any elements which are other than hydrogen and helium, essentially, right? So anything that's not in the gas component, any solids, we actually refer to that as dust. So we use that very loosely, if you like. It can be anything but it's not specifically related to sort of the dust pollution that you see.
This kind of relates to that. So what type of gas can be found in space? You talk about clouds of gas. So what elements comprise these clouds?
That's a really good question. So the most common elements in the universe are hydrogen and helium. So those are the two most common gas components that we would have. Now actually, leading on from that, there are other common elements as well. So oxygen, nitrogen, these are also common elements, carbon as well. And so it's not surprising when you think about what we are made of, in fact, that for example, water is very common in the universe, and that's simply because you have a lot of hydrogen and oxygen out there. So those are sort of the more common elements that you do have, and these might be, depending on the temperature and pressure conditions, some of them could be in solid form, some of them could be in gas form. But the most common gas elements are, in fact, hydrogen and helium.
I think this is a question a lot of us are wondering. Do you think there's another planet like Earth out there? What life forms like humans exist?
Ooh, very good question. I think now let's talk about life in the broadest context. Life in the universe, I think, is quite possible. It could possibly exist, and there is evidence for it, as there's evidence that life could exist. Now, as I just mentioned, water is a really common element, right? And as far as we can tell, liquid water is essential for life, at least for life on Earth, at least for part of its life cycle. Now, there's certainly evidence that there's water elsewhere, even in our solar system. So what I might do actually is just to bring you to a slide, which I think this is an absolutely wonderful image that was taken, I think, by the Cassini mission. And what it did was to actually take an image of the surface of Enceladus, which is one of Saturn's moons. And what you can see are these plumes of gas coming out of the surface of Enceladus. And in fact, the mission actually kind of flew through these plumes and actually detected water. So there are definitely signs for water even in our own solar system. And given how common hydrogen, oxygen, and other ingredients for life like carbon are, it's quite possible that life could exist if you have the right temperature and pressure conditions. I certainly do think that we would find another Earth-like planet. And by Earth-like, what I mean is that a planet which is about an astronomical unit away from its central star, so one that could potentially host life. Intelligent life is a different question, and that's something it could certainly be possible in terms of from a statistical side of things. If we just think about it from a purely scientific perspective, there's no reason why it couldn't occur. But that is, of course, a very important question that a lot of people are thinking about. One other thing that I will point out on that is that you do also need to have the right conditions for life. So having liquid water, we think, is one of the conditions that you need for life. And having a planet in what we call the habitable zone is very important for life too. So our planet, Earth, is in a location away from our sun where it's not too hot and it's not too cold. So this is what we often call the Goldilocks zone. It's just right for life to exist, and that's something that you would definitely need for life to try and materialize.
Okay, I think this next question kind of relates to what you answered. But was there ever life on Venus or any other planet?
For Venus, it's incredibly interesting. Venus and Earth are so similar in so many ways in terms of sort of their mass and their size, but just because of their different locations, this is actually suggests that we cannot that Venus is just not habitable at the moment. It was such that what we think happened with Venus is that the carbon cycle that you have on Earth was just simply not regulated. The fact that it was just that little bit hotter because it's closer to the sun actually meant that it couldn't have so much liquid water. And so as a result, it evolved very differently to the Earth because it was just too hot to have liquid water. Now, Mars is another interesting planet from the life side of things. It's possible that Mars had liquid water in the past. There are certainly signs that it could have done. Currently, Mars doesn't have the right kind of atmospheric pressure. So the pressure that we have on Earth is good for us because it allows life to be sustained. But Mars, the atmospheric pressure is just so low that you cannot really hold liquid water on it right now. It's just at that boundary where you can either have water in gas form, or you can have it so in the form of steam, I guess, or you can have it in solid form, so you can have ice, but you can't have it in liquid form. Now, there may have been a period of time in the past when actually we could have hosted life, we could have had life on Mars because the pressure might have been sufficiently higher in the past, but that's certainly not the case today. Now, it's worth pointing out that it's possible to have what we call extremophiles. So these are living organisms that can survive in really quite extreme conditions. So very low or high pressures, very low or high temperatures. They can even exist for a part of their life cycle without by being dehydrated. So tardigrades are an example of one of these, which appear to be able to survive in all sorts of conditions. And so it's possible that maybe there are some extremophiles that are still clinging on to life, you know, under the you know, some of the surface of Mars. And maybe it's possible that, you know, if Mars was to go through a period where liquid water could once again exist on it, not that I'm suggesting it can, but this is just a hypothetical situation, that maybe those extremophiles could then thrive again.
Okay, this next question is regarding stars. So one, do all planets orbit stars, and are there different types of stars? And how long does it take a star to form from start to its final form?
Yeah, so planets will always orbit around a star. In fact, that is one of the definitions of a planet, that it has to go around the star. In the grand scheme of things, we actually think that these processes don't take very long at all. So just to give you an idea, the disks that I talked about lasted for about they can last for somewhere between about 3 to 10 million years. For stars, we're talking about much less than much less than that. In fact, what I'm going to do is to just go back to one of the movies that I showed, and I'm just going to show you. If you have a look at the upper right of this screen before I play the movie, this is showing you 197,000 years. And if we actually zoom in to that molecular cloud, you can see that the stars really form. I'm just going to pause it. Oops, sorry. I'm just going to pause it right at the right time, and we can kind of look at what the time scale is. So I just saw the first star forming, and we're at 201,000 years. So we're really talking about a few thousand years.
Okay, I think we've run out of time. So Farzana, thank you once again for your presentation. We really appreciate you being here with us.
Thank you very much.
So before we conclude, we just want to share some exciting webinars that we have coming in the next few weeks. We have Dr. Azim Sharif speaking about moral machines, the social dilemmas of self-driving cars, and I must say this sounds very interesting, so please do join us for that. In the coming weeks, we have Dr. Hussein Rashid, who will be speaking about Muslims and popular culture. His talk is entitled Truth, Justice, and the Spiritual Way, Imam Ali as Muslim Superhero. And Dr. Shazan Mohammadi speaking about Gifts from Amin, the resettlement, integration, and identities of Ugandan Asian refugees in Canada. We really hope you guys will all be joining us for these webinars. Again, thank you for joining us today. We ask that all participants in the audience take the time to fill out a quick survey at the end, which will be emailed out to you at the end of the webinar. Again, thank you for all of you for participating today. All your questions added much value to the discussion, and we really hope you enjoyed the webinar as much as we did. If you have any questions that were not answered, please feel free to email us at the email listed below. We'd be more than happy to reach out to you. And lastly, we wish you all a safe and healthy long weekend. Please don't forget, if you require more information, support, or assistance during this time, please feel free to reach out and call the Access line. Thank you and have a great day.